All right. Thank you. Hi everyone, I'm Alessandro Lovesio from Argotec, and today I'm going to present you yet another flight software framework for SmallSat-based missions. So I'll start with a slide that looks a bit like a provocation. So why not a framework? Why not use CFS or F prime or any other framework? And actually, it's not a provocation because we did use CFS. So I could end my slides here and it would be funny, but uh, it's a bit more than that. So let's see how we got into building this framework. So let's start from the beginning. We built two missions. We started the hard way, so we started from this space. And we had these two missions. One is Argomon. It flew with the Artemis 1 mission on SLS, and it basically took pictures on its trip around the moon. And LichoCube, which flew with DART a few years ago, and it was released from the main DART probe a few weeks before the impact, and it took pictures of the impact, basically. And these two satellites were very similar. Platform was the same. Main difference was only the payloads. So the software also was basically the same. And there was no issue in reusing that. Before moving forward to the actual framework, I wanted just to share some pictures with you. I love them. I think you may like them too. So picture of the moon from behind. Kind of unsettling to me. Looks strange. And some pictures of the impact from LichoCube. And you'll say, well, it's kind of saturated. That's the point. We wanted to get the pictures of the ejecta plume so that we can get some details if you enhance the contrast. And you can get like very interesting, hope you can see it well, very interesting features on the plume. And yeah, also picture from after the flyby. Lots of interesting details that we got. Now, moving forward, after these two missions, we started development of a low Earth orbit Earth observation constellation for the Italian government under the ERIDE program. And this is a constellation of constellations, actually, and our constellation has a multispectral optical payload, which performs line scan imaging. And this satellite, while it has the same platform name in it, is very different. Unlike LichoCube and Argomon, it has two computing elements. It has still UBC, but it also has a payload processor for image processing. It has two radios, one for telemetries and telecommand, one for payload data. It's also its software is also very different architecturally. LichoCube had a very complex tracking algorithm for the asteroid. Here we don't have anything. We just do nadir pointing with some offset if we need to, and that's it. But so we had to decide whether to try to reuse the legacy software that my older colleagues built or try to do something different. And as you can see here, it was tough, but kind of easy to decide because there were so many things that we couldn't recycle, couldn't reuse. And so we decided to try to improve the architecture so that we wouldn't be in this situation again. Also because we HEO started 2 years ago, but we already knew that we would need to develop many other missions, scientific missions that are also very different in the platform. For example, Henon, which will fly in a distant retrograde orbit between the Earth and the Sun, and it will detect solar energetic particles events, where these particles apparently travel slower than the speed of light, so we can detect them and then notify Earth that they are coming. And also Lumio, which will fly behind the moon in L2, and it will detect impacts of meteoroids on the moon. And also many other missions. And I placed those pictures there because you can see that they are all very different. And while we also have a standard platform for more commercial customers, there are some performance requirements or environmental requirements like LEO, deep space, and also institutional requirements that that we can't really change. So we need to have different subsystems. We need to build a software that can work with all those subsystems so that we don't have to change it every time. So we built this new framework, which we call the NEOS. It has two meanings. I challenge you to find its meaning. And if you do, write me. You may have some gadgets to give it to you, like a bag. And so, yeah, I wanted to place here a graph where there are all the satellites that we are developing, as I said. And while they are very different, our customers still, and our program managers actually want lower cost and faster development. They can also accept little to no redundancies, maybe relaxed safety requirements, higher risks. But at the end of the day, what they really want are the lower cost and the faster time to market. And so that's what we focused on. So we tried to look into the architecture, and these are some common good architecture practices, like handle dependencies carefully, try to isolate mission-specific software, keep the firmware low, close to the hardware, isolate operating system with a nozzle, and kind of got this architecture that is quite familiar, I would say. Kind of looks like CFS, and as I said, we used it. But then we also needed some modifications because we had some additional constraints, and maybe we also thought that we could do something a bit different. So what we need to change? We heard a lot about POS. It's an European standard that we really enjoy using. It's very complex, but it defines packets also at an application level. So you don't have to think about inventing everything again. Someone else in DSS already thought about it. So we wanted to add this to CFS, but in a way that we kind of felt more comfortable with. So we changed it a bit, the message module, to do routing based on these fields. First portion is the same, but we also changed it to use the destination application ID, which for POS, it's not only the application ID in the primary header, but for telemetries, it's actually in the secondary header. So that's a bit different. And also using service type and subtype for routing, which is basically the packet type. And we also worked on NDNS independent communication because, as I said before, we now had two computing elements, an OBC, which is big endian, Leon 3 based, and a parallel processor, which instead is instead little endian. So we had to basically enforce big endian communication and have some serialization and deserialization functions to handle that. And so we got a lot of reusable modules, like for events, scheduling, FTIR, and so on, which can be easily reused, which are great. But there is a lot of stuff that kind of still was hard to reuse, like all the modules that handle the subsystems. So we tried to figure out a way to try to abstract the platform. Because if we can do that, we can avoid changes to how we test the satellites and also how we operate the satellites, both to the ground software, but I would say also most importantly to the how the team operates the satellites. Because if we have many missions, as I said before, it takes a lot more time to retrain every team to work with a very different software every time. So we worked on these two main cornerstones. One that is about services and one that is the platform abstraction layer. Let's start with that. So basically what we thought about was every one of our satellites has some basic components. Maybe have a different shape, different split in different ways, but at the end of the day, we can identify all these features. So radio modules, power modules, attitude modules, and so on. And any one of them has some common features. For example, PCDU device will always have a capability to turn on or off a device, for example. Or a radio device will have the capability to do channel configuration or selection or transmit or receive data. And maybe you can think, yeah, but some radios, for example, are transmit only. Well, that's not a problem. The interface simply is left unimplemented, but it's standardly not implemented. And there are also some functionalities that are shared between everything. For example, the right one here, the connect and initialize, some features that we always need, for example, to perform the initial communication with the subsystem and to manage errors where we need to maybe to power cycle the subsystems. And so we added this middle layer, which actually still is application layer, but the idea is that the applications above actually use the platform abstraction layer, so it comes below them. And so there is this layer that provides common set of interfaces, common set of commands, parameters that are generic, regardless of the underlying device. And so we have a generic TNTC app, for example, that selects its device implementation, given basically a sort of device tree configuration, and that device implementation provides both the common interface, which is provided for the other applications, and can also provide custom interfaces, because there will always be custom stuff. So that's allowed, of course. And then we have services, which here the idea is to help in implementing applications. We also noticed with CFS that, yeah, there is this sample app, for example, but you need to copy a lot of stuff. We had a great presentation yesterday about that. And so we try to build a library that kind of masks a lot of that activity. It allows to avoid copying a lot of code. It's just in a single place and it is used around all applications. And so with simple registration and configurations and tables, we have the ability to configure package subscriptions. We can just configure services that are available and have, for example, the subsystem connection and configuration management, which is basically a state machine with timeouts and retries and error management, which is common for all our subsystems, even though it calls different APIs, which are, however, standard. And then we have the packet routing portion, which again, it uses the underlying CFS features, but it is easily configurable with just by writing configuration tables. And so we can just decide the routing of packets from the two computing elements to ground to the debug ports very easily without changing actual code. And then we have a large suite of services. The ones on the left mostly are actually just POS services. And the cool thing is that any app can subscribe to these services. So for example, we can configure an app that has the scheduling part, and another app that has the for FDIR, which subscribes to onboard monitoring service and event action service, for example. And there are some services that instead are available and present by default on every application, for example, command acknowledgement, so that for every command, execution acknowledgements are generated automatically. And also test just to check, verify communication with the app and its aliveness. And then there is also mode management for the configuration of the platform, of the satellite, and many protocols that you know very well. And now some achievements. How did it go? Well, the framework is currently flying with the first satellite of the Io constellation, which was launched just a few months ago. We already have some very cool pictures that fortunately I couldn't show you. They aren't, we actually don't own them, the Italian government does. And what we are very happy about is the performance. It was well within our constraints, but most importantly, we think we achieved very good modularity. We actually moved to Google repo instead of the submodules. CFS comes with submodules. We used the repo in the past. We were happy with it, so we use it again. And it kind of helped also with versioning. And we think it's quite cool tool. And yeah, we just started the Hinon development. And I can say that it was very easy process. We took the HEO Fly software and we just pulled out the mission specific software. It was very easy process and took in less than 2 weeks. We had basically the basic software available to start the Hinon development. We also, in the past 3 years, developed a digital twin based using NosCube, which is kind of related to CFS, also built by NASA. And here we developed simulators for all the subsystems, and we also had the software, which is based on the same framework, both on the OBC and the payload processor running simultaneously. And we also have a ground station simulator, and that allows us to basically test end-to-end the process. So from the ground software, go through a simulated ground station with framing, with security, with SDLS, and got into the simulated radio, deframe the frames with security, and basically test the whole process. Future work. There is a lot of stuff we want to work on. I won't go through it really. I want to bore you, but the main idea here is that we just want to work on it as a software product, where we have the NEOS team working on it, improving it, and adding features, and then we have the mission team working on the actual missions, and we want to have like a customer provider relationship within our company, where we can interact in this way, where they provide us with where the platform team provides us with the framework, and we use it and we provide suggestions, that they can then implement. And to close, the idea behind what all of this is just to build better software faster. I guess that is it's like this everywhere. All of you want to do this, and this is just a way that we try to do it. We're quite happy with it. We're seeing that it works, and so yeah, we think that we can really improve the how fast we can build software. Yeah. So that's it. If you have any comments, questions, there is this QR code will bring you to a form. But I'm also here, so time for questions now, or just talk to me later.
Let's thank Alessandro. And yes, we do have time for questions, so we'll start in-house if anyone has questions.
Got one over here. Hi, great talk.
Thank you.
The idea of abstracting the families of devices like solar panels, power switching, etc. Have you indeed successfully abstracted that over multiple classes of device on multiple emissions so far, or are you still on like case number one? Out of curiosity, I'm wondering how well that worked.
Well, we don't have like a very large family of systems right now, but yeah, we started doing it. So now we have. I mean, we don't have implemented on all of them, but we know them. So what we'll have to implement them. So we made the architecture generic in order to support them once we start developing them. And right now we have developed, I think, for all the subsystems, I think at least a couple of them. And yeah, with plans to have more that we already know of. Of course, there will always be the future, some very different subsystems where we'll need to change a bit something, but yeah, when that happens, we will approach the issue. Thank you.
Right. Any other questions? All right, we do have one online question. What programming language was used?
So we used C. As I said, we worked on CFS with CFS, and it's written in C, at least for now. And we have some R&D activities where we are actually trying to integrate to have the NEOS app interface being available both in C and other languages like Rust and C++. And I think a colleague was successful in having it in Rust, but we didn't really use it for now. We didn't have the chance, but yeah, that's something we are very interested on.
Okay. Any other questions in-house? All right, I have one more quick question online.
Okay.
How do you define a generic interface between the PAL and the app layer while maintaining the completeness of the data from the device?
Yeah, I mean, we have this interface is standard for what can be standardized. So there is a lot of stuff from every subsystem that, I mean, a radio will always have some capabilities, whatever the radio it is. But as I said, if there is some very subsystem specific function, then that will be a custom interface. Because of course we want to keep the functionality, but yeah, we try to standardize as most as it makes sense actually.
All right. Well, let's thank Alessandro once again.
Thank you.